Okay, in this video we are going to start looking at some of our circuit analysis techniques. So let's do a tiny bit of review here. So remember, we're looking for steady state analysis. That's what we're doing. And what we've learned here is we have this Ohm's law type of relationship, which is that V is equal to Z times I, where Z is my impedance. So remember, this is my impedance. And this is all in phasor notation. So we're using phasors for all of this. Now, the other thing we want to remember is that for each circuit element, we have a different equation for the impedance. So for the resistor, it's simply just R. And then for the inductor, remember, it's J omega L. And for a capacitor, it is 1 over J omega C, which is the same thing as negative J over omega C. Now remember, there's also a polar format that you could put all of these in, and the polar format for this would be resistor at an angle of 0 degrees. For the inductor, it would be omega L at an angle of 90 degrees, and for the capacitor, it would be 1 over omega C at an angle of negative 90 degrees. And remember, going between rectangular and polar format can be advantageous depending on what kinds of computations you're doing in the problem. Alright, so let's continue on here with some things. Well, the thing we learned here is that, I'm just going to kind of summarize it, all circuit analysis techniques learned for resistors, the course that we learned in Circuits 1, apply for phasor analysis. So the key thing here is that and I'll kind of put it in here, the three circuit elements behave like resistors. And I'll put behave in quotes here because they don't behave like a resistor. A capacitor behaves like a capacitor. It doesn't behave like a resistor. But as far as when we're analyzing a circuit in steady state, we can treat it as a resistor. We can find an equivalent impedance. We can add impedances in series. We can combine them in parallel. We can do nodal analysis. We can do mesh analysis. We can do all of the things that we've learned before on this. So let's look at another example with this. So the circuit we're going to look at here, the question is find the steady state value for V out, and the circuit we have here is we've got some Vs here. We have an inductor, and then we have a resistor, and then that resistor is in parallel with a capacitor, and we're looking for plus minus V out here. And I should put in some values here for this. This is a 1 microfarad capacitor, this is a 400 ohm resistor, and then this is a 10 millihenry inductor. And then we also have to specify here, in this problem it specifies that Vs is equal to 10 sine of 20,000 T volts. Now, let's look at this a second here for a couple things. First off, this 20,000 here, that's the number sitting in front of T. That's always my omega. Now we want to be careful here. This is something that's easily missed in problems that we'll see in some future examples that we do, is that, and I'm going to put this off to the side and star it here. Actually, I want to put it in a different color though. So I'm going to star this here. Frequency is equal to omega over 2 pi. Or you can think of it as that omega is equal to 2 pi times f. Units for omega is radians per second, and the units for frequency is hertz. So you want to kind of keep that off in your head on the side. And the reason is sometimes a problem will say, okay, we have a sinusoidal source at 1 kilohertz. So remember, my equations for impedance use omega, so you always have to make sure you have omega when doing these computations. But when you're given the voltage source like we are here, we are always know that omega is just the number sitting in front of t. Alright, now we are going to convert all of these to phasors and do phasor computation. So let's go ahead and work on the voltage source first. Now remember, to do the voltage source here, we need this to be a cosine function. So we use the trig identity and we convert this to 20,000 t minus 90 degrees volts. And so my phasor voltage would simply be 10 at an angle of negative 90 degrees, which in polar format, that's polar format, I'm sorry. In rectangular format, this would be just negative J10 volts. And again, you want to be able to do those kinds of conversions quickly here. And if you just look at a graph here, so you got 10 at an angle of negative 90 degrees. So you go negative 90, which would take you down here, and then you'd have 10, which maybe is like right here. But then that would just be, if we're looking at the coordinates of that, that'd be 0, negative J10. And so if we wanted to write that as a complex number, that would be 0 minus J10, which is simply just minus J10 volts. So it's useful to be able to do that conversion. Now we also need the impedances of all of our components. Now the impedance of the resistor is easy because we know that doesn't change, so that's just 400 ohms. The impedance of the inductor is now j omega L, which is equal to J times 20,000 times 10 millihenries, which you get J200 for that. And then if you do the impedance for the capacitor, that is negative J over omega C, which is negative J over 20,000 times 1 microfarad, which is negative J 40. I'm sorry, not 40, I can't do computations correctly. Negative J 50. And these units are both ohms. So negative J 50 ohms. Okay, so I'm going to redraw the circuit. As I said, normally when we do these, we would have the circuit and we just relabel it, but because I'm doing this on a pad here, I don't want to have to keep scrolling up and down. So I've got my voltage source, my inductor, my resistor, and my capacitor. Now this is in steady state form, so I'm looking for plus minus V out. My input is negative J10, and then this is J200 ohms. The resistor is still 400 ohms, and then this is negative J 50 ohms. Now we should also notice here that if I look at a node right here, this node is also V out there. And so I can actually just write a simple node equation here. A single one is all I'm going to need. I could do V out minus negative J10 divided by J200 plus V out over 400 plus V out over negative J 50 equals 0. Now I'll clean this up just the tiniest bit because I'll write this as V out plus J10 over J200 plus V out over 400 plus V out over negative J50. This is equal to 0. Now, the analysis of this is exactly the same as what we did in circuits 1, but the only difference is we've got complex numbers. But we're still going to do the same thing, clear out the fractions here. So, I have a 400 here, but I'd also probably multiply through by the j as well. So I'm going to multiply by j 400. So now let's be careful here, not make mistakes. So if I do j400 divided by j200, that's 2. So I'd have 2 V out plus j20. So let's double check. j400 divided by j200 is 2. V out plus 20, j10 then, yep. j400 divided by 400, of course, is just j. And then j400 divided by negative j50, well, I still have the negative there, and that would be, again, I'm just using a calculator here to make sure I don't make a silly arithmetic error as I'm prone to do. We'd have minus j, nope, there's no j, make a mistake, j's are cancelled. It would just be minus 8 VO is equal to 0. Now we'll go ahead and move the term without the VO to the other side and then combine like terms here. So if we're careful here, we have 2 minus 8, so that would be negative 6, and then I still have plus j. VO is equal to negative j20. And now we simply just do this computation, we divide by it. And this is where you definitely want to have a calculator that can do complex numbers and that you're familiar with how to use. Alright, so I'm going to pause the video so I do this computation. Okay, so I get decimal numbers. It's not the prettiest here. Basically, I get negative 0.5405 plus j 3.243 volts. And I'm just double checking my computation here. Yeah, that's what I get. Alright, and then what you want to of course do, because we want to write this as a final answer, so we're going to want to convert this to polar. Now, and when I did that, I just had it in radians, and we typically want to have this in degrees. So when I do this computation, I get V out is equal to 3.29 at an angle of 99.46 degrees. And in general, you're gonna, you might get ugly numbers on these problems. Ugly meaning they might not work out to nice, pretty numbers, and that's because you're doing complex numbers and dividing and things of that nature. Now remember, we need to write the final answer. So this would be V out as 3.29 cosine, and then I have to remember, okay, well this is 20,000 T plus 99.46 degrees. And this would be in volts. So that would be my final answer as far as a steady state solution. Okay.